All right. Good morning, good afternoon, good evening, everybody. I'm Paul Brody. I am the Global Blockchain Leader for EY, and I want to welcome you to this digital online event, all focused around zero-knowledge proof technology. And for me, this is an incredibly important deep dive into something that is absolutely foundational to grow the world of blockchain for enterprise users around the world. When I finished university, I remember starting my first job and getting my business cards, and I was like, where's my email address? It was not on the business card. And what I was told is, we can't use the internet because it's not secure, because email messages in the good old days didn't have encryption on it. And I think to a very large degree, the same thing is true for enterprises today. When encryption came to the public internet, it made it possible to have true privacy. It made it safe for commerce, and it made enterprises feel comfortable that they could do business over the internet without putting their strategic secrets at stake. Now, of course, we're all on the internet, right? And we take encryption for granted, that it's there and it's available and it works for us. Blockchains set a much higher bar for us to achieve, because not only do we need to encrypt data, but we need to preserve the functioning of the consensus algorithm and the essentially decentralized nature of what we're trying to accomplish. And that has made kind of this whole new process significantly more challenging, but the stakes are just as large, perhaps larger, because whereas the internet was often unstructured around commerce, blockchain is all about the digital transfer of value and the execution of business contracts. So this event is all about getting the deep dive into the core technologies that are going to make public blockchains usable for all companies, especially the Ethereum blockchain. Now, EY has been investing in this space for several years now, right? And my goal in having this event today and having our amazing people kind of share, not only from EY, but from other organizations, is we want to lay out our vision, our strategic roadmap, share the work that we are doing, share how we are aligned with other kind of key initiatives that are underway, all for the purpose of getting EY and other organizations synced up together and working as one towards this shared goal. So with that, I'm going to bring up our agenda for the day, and then I'm going to give a little bit of a recap of what it is that our vision is around blockchain and where we're trying to go. So we have a fantastic agenda for today lined up. Number one, I'm going to lay out a bit of an opening vision, and then we're going to get into a series of 20-minute, very quick dives into some of the key work that's being done. We'll start with Michael Connor, who's going to talk about the Nightlight library that we've developed and have made into the public domain. And then after a break, we're going to go into two really important discussions. The first around creating zero-knowledge proofs with Socrates from the Technical University of Berlin, and then outsourcing pairing computations from Mary Maller with the Ethereum Foundation. And then we'll have another break. We'll have two more discussions. First on faster proof composition from our very own Youssef Husni from Paris, and then a dive into ZKPs from the University of California in Berkeley. And then we'll have one more break, and then we'll focus on two remaining topics, which is proving times with Aztec, and then Starkware will have a discussion. And each one of these is going to be a quick set of 20-minute discussions with a focus on, you know, what's being done now, what is the roadmap, and where the open source resource is. Then I'll be back with a brand new colored t-shirt for the wrap up. Before I go any further, I do want to make a couple of thank yous. I first and foremost want to thank Duncan Westland, Dr. Duncan Westland. He is EY's Global Blockchain R&D leader. He's not speaking today because even though he is an incredible visionary in this space, he has he's far too modest, and he is leaving the space for other people to continue. So this is this is really important that we have Duncan as a participant. And then I want to share some key links here. I want to share some key links here that people will want to make use of. So first of all, we've got the Nightlight repository, which is on GitHub. Secondly, we have a further repository on some of our deep dive materials. There's a baseline protocol, which is a big part of what we're doing, and that is available on GitHub. And then finally, If you want to try out some of the stuff that we're doing, or you want to keep up with what we are doing at EY, there's the EY blockchain website, which is at blockchain.ey.com. Right. And I want to go back and also add a couple more thank yous. First of all, to Marek Klein-Smith and Lindsay Reichelt, who have been driving our branding marketing, and then Eli Wolfson, John Frechette, and Hirko Carney, who have done a huge amount of the operational organizing and work that we have put together. So with that, let me jump in for a moment into a bit of a recap of our vision and strategy, because I think that's incredibly important just to kind of lay some groundwork. And I won't take too long in that department, because I'm very sensitive to the other far more interesting discussions going on. So,
hey, Paul.
If I sound like a broken, yes?
Hey, Paul, quick interruption.
Yes,
sorry about that. Looks like your slides aren't changing. Do you want to try unsharing your screen and resharing? Might have just frozen.
Yes, let's do that. How's that?
Yep, we can see our mission has not changed.
Fantastic. All right. So let me briefly recap here just the key links, right? 4 key links: the Nightlight repository, the Zero Knowledge Proof deep dive, the baseline repository, and the EY blockchain kind of homepage. And now let me jump into kind of my opening talk here. So our vision is really about using public blockchains to make enterprise users feel comfortable at scaling up and using the Ethereum securely for their business-to-business transactions. Our mission is something that we've been talking about for a long time, and it's very simple and it's very clear. We believe that blockchains are going to do for networks of companies what ERP did inside the single enterprise. Now, I know we have a relatively technical audience here for today's call, but I want to take a second and just talk about what is it that ERP did that was so incredibly powerful. What ERP did is it made it possible for large enterprises, ones that got bigger than 1 or 2 stores or 1 or 2 factories, for the left hand to really know what the right hand was doing, right? If you pick a piece of merchandise at a Walmart store in California, today that triggers a replenishment process that might end all the way in China, right? That's only possible because of the way ERP integrates process, organization, assets, and financial flows in a single system. And if you think about how that works between enterprise boundaries, the answer is not very well. Inside the enterprise, CEO of a company can say, listen, we are all going to use the same system. We are all going to conform to a particular process, and we're going to work together. And that has driven incredible productivity gains around the world. But if you step back and look at how this process works the minute you cross enterprise boundaries, the answer is it doesn't actually work very well at all. But with blockchains, we can start to have secure information systems that can cross enterprise boundaries in a manner that's efficient and extremely fast, right? And what that means, practically speaking, is that we think the future of B2B transactions are private, secure, regulatory compliant smart contracts that are paid and denominated in fiat currencies and are executed on public blockchains. In fact, our prediction is that a decade from now, more than 50% of the world's business-to-business contracts are going to be done on the public Ethereum blockchain, right? Now, that may sound like an enormous amount, an incredible stretch, but that model is just based on looking at the adoption rates of public cloud as we went from kind of data center computing into the public environment, right? And I think it'll be no less reasonable to think of a similar level of transformation taking place. But all of that is contingent on us adopting kind of network scalable public blockchains. Because private blockchains, time and again, what we learn over and over is they don't have a scalable kind of an enterprise networking model, right? They tend to end up with small groups of suppliers and partners working in a particular siloed environment, a logistics network or an insurance network or a retailer's particular traceability network. And sure enough, when we did our survey last year, we commissioned Forrester Research. What they told us, what we found out, was that the average private blockchain has 0.5 participants other than the founding company. And the reason for that is that although lots of companies, a small number of companies are willing to join consortium and a medium number of companies are willing to join somebody else's network, almost everybody wants to start their own network and be in charge of their own fate, And this is a problem that's kind of almost universal in the business community. Everybody wants to have control, right? And the reality is that if everybody wants to have control, it doesn't work, right? What does work, and what's been incredibly encouraging, is that what we found over and over again in talking to executives is that they are learning from this experience. And so now, if you ask people who have actually implemented blockchain in their enterprise, 75% of them will tell you that they believe that public blockchains are the future. Because if they can't have absolute control, the next best alternative is to work in an environment where their competition also cannot have control, right? And this is, I believe, the kind of the incredible leveling power of public blockchains. Now, the foundation of all of this to work is privacy and business logic, privacy and data transfers. We've spent a lot of time and energy working on this, right? Starting with our original product, our kind of prototype that we launched back in October of 2018. And then, gas cost for us was $100 for a single transaction, and that was not scalable, but we had kept at it. We introduced a solution, an open source public domain solution in 2019 called Nightfall, and we got it down to about $10 a transaction. And by the end of last year, we had it down to about 5 cents a transaction by throwing in batching and making use of other significant improvements that we'll be talking about today. Very importantly, since then, we've also been working on maturing this process to support regulatory compliance rules. So allowable business partners, not allowable business partners, audit functionality. And one thing that people get confused about a lot, and I sometimes think that people who don't love blockchain, they deliberately want to confuse the issue. They want to talk about privacy as if that's the same as anonymity, right, for illegal activities, versus the privacy that enterprises need in order to do business without their competition seeing what's going on. So this, for us, is really important. We want to provide business users with the maximum level of privacy that is consistent with regulatory compliance. We're not in the business of sort of unlimited privacy and anonymity. We're in the business of secure enterprise transactions that are regulatory compliant. And that's a really important theme. The second thing to put on top of this is that transfers are not enough. It's great that I can pay you, but if the terms and conditions of our business agreement are not private, then it's no good. If everybody knows that I'm buying mangoes from you at 50 cents a piece, I've already disclosed at least half of the most important information that we're sharing, and the other half is how many. And okay, I can do that transfer privately, but you've already shared such incredibly sensitive and important information. So we need to do more than just have private transfers. There's a lot of work left to be done around zero knowledge proofs. And at the top of that list is private business logic, right? We need to be able to say what the rules are, how we are going to work together as a set of enterprises. That, for me, is probably the top of the list. There's other stuff that has to be done, things like that are not necessarily dependent on zero knowledge proofs, but are critical for making the business ecosystem run, which means business identity and discovery, right? Who are you actually dealing with, right? This is a particularly important issue. Synchronization of your process state. So it's great that we have similar information, or we have a similar shared agreement, but we also need to synchronize some of our core enterprise data, right? If you're in the world of enterprise computing, message queuing, data synchronization is an essential part of what you do. It is also an essential part of what's going to get done between enterprises. And then finally, tokenization. So one of the most important things that needs to be done under zero knowledge is a proper tokenization of inputs and outputs of the business infrastructure model that we're trying to create. My goal, our goal, isn't just to enable 3 or 4 companies to transact with each other privately and securely. You don't actually fully need a blockchain for that. What we want to be able to do is to make sure that the inputs and outputs of that process can be packaged up as standardized digital tokens, things like invoices, purchase orders, leases, other types of assets, and they can then be plugged into the DeFi, the decentralized finance ecosystem, right? Our goal isn't just to create a set of private networks that are stitched together with a blockchain. Our goal is to create a secure private infrastructure that enables a whole business ecosystem, right? Where at the click of a button, not only can we have a business contract together, but we can actually have a I can factor my invoice, I can get working capital, and I can do that without a huge amount of actual paperwork. So that's kind of the vision behind the work that we are doing, and especially the collaboration we established with Consensus and Microsoft to create the baseline protocol. And we'll be talking a lot about that vision. How do we get there? For me, this is kind of incredibly important, right? It's great if EY gets there by ourselves, but that won't lead to a real transformation, right? If we think about how cloud and all other kind of computing technologies have really taken hold, it's always as public standards. It's always as something that's adopted and shared widely. And so our goal today is to do a lot of public sharing of our roadmap, some of our thinking, some of our best research, right? That's step one. Number two, we are sharing our progress and we are inviting others to join with us, right? We can't, shouldn't, and don't want to do this alone. We want to bring enterprises and leading thinkers along with us, because the gold standard for security isn't just that you have open source code, it's that you have open source code with a robust community and ecosystem that is constantly inspecting and improving it. And then finally, I want to reiterate our commitment to public domain information, public domain licenses. So in other words, no licenses, no surprises, no gotchas, right? Nothing you need a team of lawyers to sit through. You can use it however you need to. And our commitment to open source, right? This is, yes, we're a business. Yes, we want to see this technology mature and we want it to drive business for EY. But at the most foundational level, if it isn't a shared effort, if it doesn't become universally available without lots of strings and complexity, then we know it will never get adopted. So I really want to emphasize again, our commitment to releasing strategic assets, millions of dollars of R&D work as public domain resources that are fully open source. That's pretty much it for me. I am going to hand over the reins in about 1 minute to my colleague, Michael Connor, who's going to talk about programming zero-knowledge transfers with Nightlight. Nightlight is a successor to Nightfall, and it's a way of making this kind of work much, much easier. I want to thank everybody who has joined us today, and I want to reiterate kind of our commitment to the public Ethereum blockchain, to the work that we are doing with the baseline protocol. And with that, I will hand it over to Mr. Connor. Mr. Connor, thank you for joining us.
Thank you. Hi, Paul. Okay.
All yours.
Thank you. I'll take it away. Okay. Just sharing my screen. Okay. So yes, as Paul said, I'm Michael Connor. I work in the EY blockchain R&D team. We're based in London, although we're all over the planet at the moment because of coronavirus. Today, I'm going to talk about making dApps, decentralized applications for public blockchains, how to make those private. So there's a lot of existing blockchain applications that have been built over the last few years over the Ethereum blockchain, decentralized finance applications, all sorts of really useful blockchain applications. But the problem, or rather an issue that businesses have with them, is that lots of data is private. So businesses at the moment can't use those applications as they are because they might reveal data when they do blockchain transactions. So today's talk is going to be, well, can we take all of this existing infrastructure and can we plug in privacy somehow so that we can keep all of this great work we've done over the past few years, but just make some of those public inputs private so that businesses can use existing things on the blockchain. So the agenda will be, I'll introduce Nightlight, which is a tool that's been built by EY Blockchain. It's a library which should help existing app developers make their applications, their ERC-721 contracts for non-fungible transfers, or their ERC-20 contracts for fungible value transfers, make those applications private. I'll then hopefully give you a demo, a very simple application. We'll start with a bare bones ERC contract, and we'll try and add Nightlight to it to make it private. And then finally, something I'm really excited about is, well, what beyond transfers? So a lot of talk with zero knowledge proofs is how to do transfers privately. But of course, Ethereum unlocks a huge possibility for smart contracts generally, so general computation over a public blockchain. How can we make general computation private? How can we have private contracts more generally over Ethereum? So we'll look at that quickly at the end as well. So a bit of history. About a year ago, EY released Nightfall, and we released it into the public domain open source, as Paul talked about. So we gave everything away, hoping that collectively we can get businesses closer to using the public blockchain sooner. And what did Nightfall do? It was a full application that enabled private transactions over Ethereum. And the technology it used was ZK snarks. Now, what I won't be doing in this talk is going into how ZK snarks work. That's quite a hefty subject in itself. So who's this talk aimed at? Well, it's aimed at perhaps app developers, blockchain app developers in particular. It might be applicable to applied cryptographers, and indeed, hopefully, anyone who's interested in blockchain or privacy in general might take something away from this, hopefully. But the problem with Nightfall was that it was a full application. It was a huge suite of tools. Well, that was an intentional feature, but what we want to knuckle down on now is how do we plug privacy into existing dApps? If we take a look at Nightfall, it's got lots of components to it. And the components on the left half are ones that a conventional blockchain developer might already be familiar with. So we have a user interface, authentication, so allowing users to log in and control their account, access to an Ethereum client, Geth parity, something which can communicate with the blockchain, grab data from the blockchain, and invoke transactions over the blockchain. Most applications, or at least the ones we care about for this talk today, will have ERC20 or ERC721 contracts, where public transfers can transfer ownership of goods or underlying assets. And then your application might also have Ethereum account management, so the ability to handle gas, to pay for those transactions, and a database to tie everything together so data isn't lost. What Nightfall really brought was this right-hand side to enable private transactions. So we've got private transaction logic, so the difficult cryptography, the unusual things that an ordinary blockchain application might not have to handle. So cryptographic commitments, Merkle tree inclusion proofs, creating ZK snarks. We use Socrates, and the next talk will be by Jacob and Thibaut. They'll be talking about how to use the Socrates toolkit. Well, Nightfall is a wrapper around that toolkit specifically for doing zero-knowledge transfers. What else does Nightfall include? It includes private contracts. So alongside your ERC20 or ERC721 contract, you deploy an extra contract called the shield contract, and that enables you to hold tokens in escrow while private transactions happen behind the scenes. And finally, something that's often overlooked, or at least mentioned less, your application will need to handle all of this extra private data. So when you create your private application, all these cryptographic commitments, extra public keys, which are efficient to generate from a secret key within a snark, Merkle tree stuff, it will all need to be contained in a database securely in your application. And you'll also need to do private messaging. So whereas conventional blockchain applications might glean a lot of their data from the blockchain because it's public data, who owns what can be seen. Well, if we design our application to hide from the blockchain who owns what or what can be seen, in order for me to inform the person I've transferred money to that I have indeed transferred money to them, I'll need a private messaging channel, and Nightfall has that. But what we found is existing blockchain app developers don't necessarily need this full suite of tools. What they prefer is for us to extract the important tools that they might not have the expertise or the time, or they might not have the funding to produce. Well, hopefully Nightlight is a pre-built library of tools that will enable those blockchain developers to get their apps private more easily, more quickly. We also have extracted Merkle tree logic in a separate repository called Timber. So these are two new things, Nightlight and Timber. And again, they're open source. So Nightlight comes as an NPM package, or you can visit the EY blockchain GitHub page, and you can take a look at the source code, do with it what you want. Again, it's all open source, public domain. Timber, again, open source, public domain, again at EY blockchain. So what I'll try to do now is I'll try to demo how we can take a very bare bones decentralized app and try to make it private. And I'll specifically look at an ERC 721 contract. The most famous example being CryptoKitties, where you can transfer non-fungible tokens. But of course, for business applications, underlying assets in supply chain, ERC 721 tokens would be pivotal to those as well. So what we're going to look at is we're going to look at how we plug Nightlight into that application so that we can inherit all of the private transaction logic, the ZK Snark proof generation tools, so that we can attest to the fact that we wish to transfer value, all these extra private contracts that your app wouldn't ordinarily have, and also Merkle tree logic. We're going to try and look at an example to handle all of that. So what I can do now is I can switch over and we can take a look at Atom. Let's take a look at the code. So first we'll look at the existing bare bones app that we might have. So on the left-hand side here, I've pulled together a demonstration app and something that conventional blockchain developers would be familiar with is a non-fungible ERC 721 contract. So we'll start looking there. And we can see this NF token contract is an ERC 721 interface contract. So it adheres to all the standards. This was taken from the Open Zeppelin library. There are other libraries available that have been security reviewed that you can work with. And this has familiar looking public transfer functionality. So we can take a look here. Here's the transfer function. And you can see that the person you're sending money to and the token ID are public. Everyone would be able to see who you are sending funds to. And so what we add to that is this privacy set of contracts. And you can find these privacy set of contracts in Nightfall or Nightlight. And if we compare the two, we compare the transfer against, for example, a public the private shield contracts transfer function, we can see that in the shield contract, there's less intelligible information makes its way to the blockchain. Instead of the person you're sending to and the thing you're sending, what instead gets sent is a proof, some inputs, which contain nondescript items like the root of a Merkle tree, a nullifier, and a commitment. And if you're a conventional app developer, you might not know necessarily how to call this function, how to interact with this contract, how to generate a proof. And that's where Nightlight comes in. So Nightlight has the tools to allow you to interact with these extra contracts so that users who already use your application can instead use your application in a private way to transfer. So if we take a look at the JavaScript code which underpins this within our simple application, well, we have conventional getter and setter functions to interact with this regular public contract on the right here. So getting things, invoking minting, invoking transfers. Well, what we can do, and I've created a demo script, we can import Nightlight, the set of tools, so that we can interact with the shield contract. And here, if I scroll down, we have tools to invoke a private mint via Nightlight. And the information we pass to the mint function is information your application will already be dealing with: token IDs, public keys, Ethereum account data, and then there's some information that is contained in the Nightlight documentation that is easy to send back and forth to the Nightlight application as well. What does Nightlight do with that information you send? Well, it will create cryptographic commitments for the user. It will open up a Socrates container. It contains pre-built arithmetic circuits to generate a proof which attests to the fact that your user wishes to transfer ownership of their funds privately. It will then send that zero knowledge proof, which is just elliptic curve points. It will send that to the blockchain, those pre-built shield contracts. Those shield contracts will verify the zero knowledge proof. That doesn't cost much gas. We've been working to bring efficiency down, like Paul said. And then once that proof verifies, the commitment will be stored in a Merkle tree on chain, and it will return to your application basic data which you will need to store in a database. But most of the heavy lifting is done by Nightlight, which is great. Now, your application might include more detail. It might have a user interface and all these extra things that traditional applications have. And another thing you'll need to handle is private data and private messaging tools. But Nightlight's documentation makes it easy to know which information you need to send to the Nightlight library and the kind of information you'll get back and how securely you will need to store that information, particularly private keys which get passed into the ZK snarks will need to be stored in a very secure database by your application. So how do we install Nightlight? Well, it's like any other NPM package, npm install Nightlight. And indeed, within this application, in order to import the functionality of Nightlight, we have included Nightlight in our package JSON. Another thing that snarks have is verification keys and proving keys. And we use Socrates to generate those for us. And Nightlight includes a very simple function, generate Socrates files to do that trusted setup for you. Or if someone else has done a trusted setup and already deployed a Shield contract, then you can utilize that. So without further ado, I will jump into doing a demonstration. So what I'll be doing is deploying this simple application with all of the Shield contracts around it. And I'll do a simple, I'll do a simple mint, create a public version of a token. I'll then transfer that token to a Shield contract and receive a private representation of that token. And then I'll do a private transfer. Okay, so we'll start our containers and we will migrate all of those contracts to the blockchain. So what we're doing now, within containers, we're starting up a local instance of a blockchain on my laptop in Ganache, and we're deploying contracts, a cryptography library, a ZK snark verifier contract, a Shield contract, and the ERC721 contract. Now that's all been deployed, I will start the rest of the application with Docker Compose. So the rest of my application is starting now. Okay. So what's happening now is I'm deploying verification keys to the smart contract, to the Shield contract, using Nightlight. So it's Nightlight which is handling all this logic for us. And Nightlight is also subscribed to the Shield contract, listening for any new commitment leaves being added to the Merkle tree on chain. What I'll do now is I will have a look at the containers we have running. So we've got our app, we've got Timber, our Merkle tree instance, and we've got Ganache. What I will do is I will jump into the container of our app. Okay, we're inside. If we list everything, we've got everything we were previously looking at in Atom, and we've also got Socrates, which Jacob and Thibaut will be talking about later, so we can generate zero-knowledge proofs. And then we'll just run the demo script. And again, this demo script will mint tokens for us and transfer them. So what we're doing now is we're initializing demo values, and we've successfully minted a token. We've minted a pizza token with a token ID for a public account. Now, this is all public information that your conventional dApp probably has all at the moment. But then we've called Nightlight, and all this debugging information in green here is information and calculations being done by Nightlight on behalf of your dApp. And what it's doing is it's creating cryptographic commitments, and it's currently, as I speak, generating a zero-knowledge proof, attesting to the fact that me, the user, wishes to create a private representation of my token. And there we go, there's my zero-knowledge proof. It's just 3 elliptic curve points. And it's sent it to the blockchain, it's minted it. We used mimic hashing rather than SHA-256 hashing, so the proof generated more quickly. And we've minted our token. The next step is to invoke a transfer. And again, we just send simple data to Nightlight. It does all the heavy lifting, creation of commitments, proof generation, and communication with third parties. It creates a Merkle tree membership witness, and then it sends the transaction to the blockchain after it generates a zero-knowledge proof. So what I'd like to stress is the fact that Nightlight does all of the heavy computational lifting. And if we shimmy back to our slides, Hopefully it makes it easy for you as app developers to implement privacy into your application. Feel free to dive into the code. Feel free to open issues on GitHub. Feel free to ask questions. We're always keen to have conversations to improve our tooling. And we're also keen to collaborate with other people on other projects. You know, if you have other privacy projects that might help our clients, businesses achieve private transactions or private contract execution on the public blockchain, if your project might help us get to that quicker, we're always open to collaboration. It's really exciting. The final thing I want to talk about is what next beyond transfers. So lots of ZKP presentations and lots of literature when it comes to blockchain focuses on just transferring ownership of fungible and non-fungible goods. But as Paul alluded to, we might be, well, we can use the Ethereum blockchain to do more complex smart contract transactions. So business agreements, the terms of those business agreements can be encoded in smart contracts. But still, the problem with that is that some of the underlying data can be seen on the blockchain. So can we deploy private contracts to Ethereum where invocation of the functions is private, the data being sent to those functions is private, and no one learns what function anyone is calling? Well, it turns out we think we can, and we're working on a project at the moment that we're hoping achieves that, where the terms of a contract are private, invocations of any functions, any transactions are private, so no one learns what function you're even calling. So if you're a business and you want to send a shipment, even calling that shipment declaration function would be private. But nevertheless, the terms of those contracts can be enforced, and they would be enforced through ZK snark verification. So what we're working on at the moment, on top of the EVM, is something we're calling a ZVM, a ZK snark virtual machine, or a zero knowledge virtual machine, which facilitates this gateway where any function execution is private. No one learns what functions anyone's calling, which is really, really exciting. We're going to release a midnight client, which is a gateway for users to interact with the ZVM. And therefore, beyond transfers, we'll be able to invoke any private smart contract logic. More coming soon. What technology will we be using to achieve that, and are we using to achieve that? Well, Zexy, the groundbreaking paper on zero knowledge execution, we're working with ideas from that paper. We're working with the elliptic curve that Youssef and his colleague discovered, and there's a talk from Youssef later today as well. And we're working with the Socrates teams to add those elliptic curves to our project. So really exciting stuff that we're working on. Hopefully we'll be able to talk more about that soon once we finish some of the coding. So with that, I will stop my talk. But thank you very much. Please feel free to reach out. Please feel free to ask questions, open issues on GitHub. And as I say, we'd welcome any contributions from the community. Thanks again.
Thanks, Michael. So we've got a few 5-minute breaks scheduled throughout the day. Right now, we'll take probably 5 to 7 minutes, just so everyone can sort of catch up on emails, or of course, ask questions if you have any. I see Duncan's been really active with answering emails in the Q&A portal, so now's a good time to get them in. Thanks, everyone.
Okay, hey everyone, I'll take over screen now, and let me know in case you cannot see it. So the slide should be live right now. All right, then let's start, let's kick it off. I'm Jacob, with me is Thibaut, and we're glad that we can be here today and talk about Socrates. We called the talk CK Snarks for Developers, and that's exactly the goal behind the project as a whole and the goal of this talk today. We've heard a lot about the motivation today already in excellent talks so far. And I think by now, probably everyone agrees that privacy is one of the big outstanding challenges in the context of public blockchains. And Socrates is a project that set out to address this challenge by allowing developers easy access to CK snarks so they can improve privacy of their dApps without becoming cryptographic experts first. So Socrates is supported by the Ethereum Foundation and was started by me as part of my research at Technical University of Berlin, and is now used by a couple of projects. And we're also very happy that EY has been building Nightfall on top of it, has been using it as part of the baseline proposal, and is now, as we've just learned, building a very cool, even more generic privacy framework on top of it. And they've been also collaborating with us on the latest releases. So that's a very nice collaboration going on there. So what is Socrates about? What's the motivation? We've seen, for example, how Zcash innovated on Bitcoin by adding privacy, and Ethereum allows developers doing much more generic things, having much more complex state transitions functions, building powerful decentralized applications that can do all kinds of things. But one of the big blockers, besides cost of on-chain transactions, privacy has been an issue, because all the information that goes into state transition has to be published to the blockchain. And the idea behind Socrates is to provide developers with a higher level abstraction so that they can leverage CK snarks or zero knowledge proof in a more abstract sense to address the privacy needs in Ethereum-based applications. And I think in the previous talk by Michael, we've seen excellent examples of what that can look like and how they can even be an additional intermediate layers that really enables developers to unlock the benefits. So what is Socrates? Socrates is basically a framework and has a set of components. It has a high-level language, so it's a programming language that is domain-specific and that you can write off-chain computations in. So you can run on some blockchain external node, and then you can send the result to the blockchain, including a proof that shows that this computation has happened correctly, and there hasn't been any cheating or any tampering with the result. And so Socrates has that language and includes a compiler which allows you to transform programs written in that language into provable constraint systems that are provable with CK snarks. And CK snarks, because they are just very efficient with regards to verification. There have been prototypes where Socrates has been used for bulletproof backends as well, for example, but their verification's more expensive. And there's a lot of new cool schemes coming out of research that we're also closely looking at and considering adding. But for now, CK snarks, with their trusted setup assumption, they just offer very, very cheap verification, which is kind of a key enabler for today's on-chain verification. So we support different backends, but this talk's not about these technical details. This talks about showing you what it can do on a high level, and then going into a hands-on part where Thibaut will demo how we can actually use Socrates to write CK snarks in a way that is accessible to regular dApp developers, so they don't have to learn about the low-level cryptography to unlock the potential of that kind of tech, which is quite hard, to be honest, and takes a lot of effort and time to understand well enough to be able to do something useful. So that's kind of the gap we're trying to bridge here. So Socrates provides us with tools for setup phase, witness computation, proof generation. Long story short, all the steps you need to do to execute off-chain computations with ZK-SNARKs. The language is an imperative domain-specific language, has kind of Python-inspired syntax, and it does not expose any of the intricacies that ZK-SNARK programming usually has to developers. It has some primitive types that you can use, and also has more complex types like structs that are user-defined, like lists and arrays and these kind of things. So it's a programming environment that regular Solidity developers should be comfortable with in no time, pretty much. The process of executing such off-chain computations depicted here, we'll do that hands-on in about 2 minutes. And we always start with the program written in the Socrates language and then compile that to an intermediate representation, which is an arithmetic circuit, basically, but enriched with some information that makes the processing more efficient and in a way that we can easily find the witness, which is basically a satisfying variable assignment for the generated arithmetic circuits. And then after the setup step that I previously mentioned, we can then, for that execution of that off-chain computation specified as a Socrates program, generate a proof that shows in zero knowledge, so without exposing detailed information of any private inputs to the computation or any intermediate results of that program's execution to the blockchain, using ZK-SNARKs. And then the tooling also allows us to support, export verification Solidity smart contract for the given Socrates program. And then that can be deployed to the Ethereum blockchain and used to receive proofs and computation results. And it then verifies those proofs and accepts the result if successful. To support developers with common tasks in the context of blockchain-based applications, there's a standard library that provides us with all kind of the things we need for privacy engineering. For example, that's an implementation of elliptic curve cryptography and an EDDSA signature verification function that can be used. There are several hash functions, depends on what kind of assumptions you have, whether you're using it for commitment schemes or for other purposes, whether you want to recompute hashes on-chain or not. So we support char and different variants, Peterson hashes, and the MIMC class of hash functions as well. And some work in progress highlights before we dive into the hands-on demo are that we're currently working with the EY folks to include recursive proofs based on the SEXA integration that we'll also have a talk later on. We're working on more generic programs so that we don't have to adapt our programs for different problem sizes as much. We're adding more types and also better developer support, basically by allowing simplified project configuration and even better usability for non-expert users. Thibaut, take it away, please.
Thank you. Hi, everyone. I'm just going to share my screen now. All right. I hope everyone can see this. So I'm going to showcase the workflow of Socrates that Jacob just mentioned. And for that, I'm going to use the online IDE Remix, which was originally developed for Solidity, but now supports also Socrates. So the first thing that you want to do is to activate the Socrates plugin. Here, I'm using a plugin that's slightly more experimental as I want to showcase some of the new features that we've been working on. So the first thing that I'm going to do is to create a new file that I'm going to call main.zoc. And here, the program that we're going to make is going to be very simple. And basically, it's going to require the prover to find the square roots of a number which is public. So you have a public number, the prover finds the square root of that number and proves to the verifier that they know this number without revealing it. So in Socrates, the way you do this is by defining a main function, which is going to have 2 arguments. The first argument is going to be what I call the target, and this argument is public, and the second argument is going to be private, and I'm going to call this one the root. What we're going to return is a Boolean, which will be true if the condition that I just explained holds. As you can guess, this program is going to be very, very simple, as we only have to return this Boolean. Right, so that's the whole program. Now, in order to compile the program, I'm going to use the Remix plugin for Socrates and just click compile. Oh, I forgot an equal sign here. So we have a successfully compiled program. So once the program is compiled, the next step is execution. And then for execution, we can provide arguments for each of the two arguments. And in this case, we can have, for example, proof that the square root of 4 is 2. And if I compute this, I can see that the Boolean return is this. And if I, for the sake of the example, change the value here, we can see that it returns false. However, at this point, the only thing we've done is executing the program on the prover side. However, we have a verifier on the other end who needs to be convinced that the prover actually knows this value here too, without this value being revealed. So that's where the zero knowledge aspect comes into play. And for that, with the proof system that we're using, we need to first run a setup, which I can do with this button. And what this does in the background is that it creates a proving key and a verifier key. Both of them are public, so there's no requirement on keeping them secret. However, the proving key is going to be useful for the prover, and the verifying key is going to be useful for the verifier. In the context of blockchain, in a lot of cases, the verifier is not actually a human, it's rather a blockchain. So we're trying to convince a blockchain that as a user, we did some action or we know some data that we're supposed to know. Therefore, the verifier itself is going to materialize as a Solidity contract. And you can create it here based on the verification key that we just created in the setup phase. And I can actually open it here in the Remix editor. And this is generated by Socrates for you based on your particular program and your particular instantiation of your keys. So the next step in this case will be to actually instantiate such a verifier. And therefore, I'm first going to compile the verifier. And using Remix, I can, using the execution in Remix, I can actually deploy this verifier, which is now deployed to the EVM that is running locally on my machine. So that's the JavaScript VM. And this verifier exposes a single function, which is public. And this function does something very, very simple. It takes a proof as input and returns a Boolean true or false, whether that proof is correct or incorrect. So we have our verifier ready. Then the next step in the process is to basically take the result of our computation, which was here correct. So I'm going to compute it again. We have a valid square root. And based on that and the proving key, I can generate a zero knowledge proof. And this zero knowledge proof is here in the form of parameters that I can pass directly to the verifier. So we can go ahead and go back to the Solidity, to the EVM execution tab and pass those values to the verified transaction. Actually, there's a slightly better UI here. You can see actually the shape of the zero knowledge proofs that we have. So you have this 3 values ABC, which are elliptic curve points, as well as your input, which is the set of all your public inputs in your program. Therefore, your square root will not be in this set. I can now call the verifying function here on the EVM. And I get here in the logs this call. And if we look very deeply, maybe that's a bit small for some of you to see, but we have decoded output bool true. For the sake of the example, we can try to modify slightly the input that we give, trying to, for example, claim that 2, which is our private value, is the square root of 5 here. If I change the input, and I can call this function again. Takes a bit of time. And we have a result here again from this transaction, which returned false. So this is the general workflow that we have to deal with to create those neural knowledge proofs. Now, very quickly, I'm going to show another small example without going through the whole process, but maybe something a tiny bit more advanced that you might be interested in if you develop with zero knowledge proofs. So in the previous example, we were just proving that we knew a square root of a number, which is reasonably easy to compute. However, in a lot of cases, when we're dealing with commitments, something that's really, really useful is to prove that we know the pre-image of a given hash. And that's what we're doing in this case. So in this case, I import a function which is provided by the Socrates standard library, which basically is the SHA-256 function applied to 512 bits of input. These inputs have a slightly different format that you would expect in general, but I'm not going to go into that. But basically, the program itself has a very similar shape to the one I showcased before. You have a public value here that you provide as 256 bits, which is the hash that you're trying to target with your pre-image. And you have a private pre-image. And then inside of the program, you basically rehash the pre-image and check it against the value. So I can quickly go here and compile this other program. So this program takes a bit longer to compile. Here it's compiled, and basically I'm not going to go through the whole process, but here if I provide some values, let's say 0, 0, and here all zeros, we can see that 0 is not the pre-image of 0 by SHA-256, which is actually a pretty good news for the hash function. And from there, I'm going to give it back to Jacob for a conclusion.
Okay, thanks for the demo. That worked well. So if you want to play around with the tooling, you can just use the in-browser IDE as we just did. So go to remix.ethereum.org and enable the Socrates plugin. Furthermore, if you are interested in getting in touch, we're looking for people from the community who are interested in Rust development, because all of our projects written in Rust pretty much. People who are interested in state-of-the-art cryptography, integrating new schemes, playing around with things, we're very open to that. And just people with a general interest in programming languages, in new domains. We're very just happy if people get in touch and see whether they can contribute on a conceptual level, on a coding level, whatever works. Here are some more resources for you to check out in case you're interested. Also check out Nightfall and Baseline. The top link, socrates.github.io, refers you to our documentation, also includes nice getting started examples. And if you have questions or would like to interact, come to our Twitter channel. That's it from our side. Thanks for listening. And yeah, I think we'll jump to Mary now.
Thank you.
All right. Thank you both. So I think next we'll have Mary Mahler coming up. And Mary, if you want to start getting your presentation set up, and whenever you're ready, you can share your screen.
I'm going to assume everyone can see that okay.
Yes, we can.
Great. So today I'm going to be talking about a work we've been doing, which we've called inner pairing product arguments. But the general idea is that we want to be able to aggregate lots of data in a way that is very efficient to verify, and also maybe a bit quicker for the actual person who's doing the aggregating than your usual SNARK solution. I'm going to spend the first part of my talk motivating what I mean by this aggregator and where it would be useful, what are the pros, what are the downsides. I'm then going to talk a little bit about trusted setups, because I believe our solution is a lot better when you are willing to accept a trusted setup. And I'll finish, if I have time, talking about the potential privacy benefits we could also see. So one theme that we're going to see a lot today is that SNARKs can be used to scale blockchains. So with blockchains, you have lots of issues to do with data storage and verifier time, in the sense that all data has to be seen by all of the full nodes at least, and they have to check every single state transition which is happening is being done correctly. And you can definitely envisage a situation where this can be done a lot more quickly, and as has been proposed by several roll-up projects, where just one person sees lots of the data, lots of these transactions. They compute what the state change will be, and then they just broadcast the state change plus some proof that they have performed this action correctly. So how a SNARK would do this is, what a SNARK does is it takes in a computation and it provides a proof that the output of that computation is correct. So we have two security properties. The most important one is soundness. If the result is wrong, then no prover can convince an honest verifier it's not doable. You can also have a zero knowledge component, which is useful for privacy solutions. But I'm going to start by talking a lot more about soundness, because that is relevant for both scaling and privacy solutions. Soundness is also the harder of the two properties to achieve in general. So with a SNARK, you have a situation where proving, generating this proof that your change of state has been done correctly is very expensive. So expensive that it might put people off doing it. But verification is very cheap, significantly cheaper than running the computation itself. And proof sizes are also very small, so you're not having to store lots of data. And one nice thing that we have is that if you have a dapper privacy solution which is using SNARKs, you can build a SNARK of a SNARK. So this is also something which we are able to aggregate, and if you have lots of stuff being done at the same time, do it a lot more efficiently. Methods about how to do this have been known for quite a while. I think the first really big relevant work was on cycles of elliptic curves back in 2015. But for 128-bit security, these curve sizes are bigger than for normal SNARKs. A lot of work has been put into improving these solutions as well, including some talks which we'll see later today. But the big downside to this approach is that if you wanted to represent your computation using Socrates for the computation of a SNARK verifier being satisfied, then you're talking about an overhead of at least 1,000, 10,000 even, per SNARK proof. And actually, I think in practice, once you've actually done all of your group exponentiations, it might be more than that. So we're in a situation where our transaction aggregator is going to be very, very expensive. It's going to take several minutes to run, I would expect. That's a guess, though. So our more recent solution is to use an inner product argument, which is a type of zero knowledge argument, really. But here we have that the aggregation process, the actual proving time, is going to be much faster. So we're thinking an overhead of 6 compared to natively verifying the snarks. Verifier time can be logarithmic with a trusted setup. Without a trusted setup, we still get some fairly significant savings, but nothing on the asymptotic level. And one downside really to our work is it only works with more classical snarks like GROT16, GM17. It doesn't work with the more recent ones. Another downside is that we do need target group operations. And currently, in Ethereum at least, there aren't any precompilers for target group operations. I'm pushing for them a bit. I'm hoping that they'll come through someday soon. And there is an explanation, a guide on how to implement these in Guide to Pairing-Based Cryptography. Also, it's been implemented in the Sexy code base. So I've been talking a lot about how there's 2 solutions really if you're wanting to aggregate snark proofs. Either you can have cycles of curves, or you can use our approach with an inner product argument. Some of you might be thinking, if you're really following my talk very closely, why can't you use both? And largely the answer to this is that maybe you can. We haven't implemented it, we haven't experimented with it, we're not sure whether it works, but we feel like there's a good chance that it might. So you could take together our work on, say, aggregating GROT16 proofs, and then you could represent that verifier inside Socrates or your circuit for proving your computation and prove a snark for that. And that could get you the best of both worlds. You could have the situation where you've got small proofs and small verifier time, but also a much faster prover, hopefully. I'm also hopeful that this kind of approach might be helpful for data availability proofs. This is another buzzword that the Ethereum team have been worrying about a lot lately. They want to be able to generate fraud proofs such that clients can have more faith that the full nodes are providing correct information, because if they're not, somebody can provide a proof that they're not. But then they run into an issue that if the data is not available, then how can you prove that someone hasn't behaved honestly? And these data availability proofs are not an easy thing. Certainly we haven't yet found something which would be efficient enough to use in ETH 2.0, but people are working very hard on that. So hopefully we'll come up with something reasonable. And I definitely think that this approach would not be would be worth looking at, because if you have a Merkle tree with lots of snark proofs that things have gone through efficiently and you want to just verify them all in one go, that is something we're able to do. So I've mentioned that our solution is most efficient when we have a trusted setup. The most commonly used trusted setup at the moment is one called Powers of Tau. This was sort of initialized by the Zcash group. So if you have a trusted setup snark, then we're not able to build proofs without first running a setup ceremony. And the idea here is that if a single honest participant takes part in that setup, in that ceremony, then the resulting snark will be secure. But if each and every one of the participants is adversarial, it won't be secure. There was a little bit of controversy over the very first setup that Zcash ran, which was largely to do with the fact that they only had 6 participants. But in the more recent setup, they got 87 participants, which seems more reasonable than 6. And the counterfeiting bug, which if you don't know about it, this was a bug that was found, which meant that if somebody knew about it, maybe they were able to print money. That was not because of the trusted setup. A similar mistake could have been made using any zero-knowledge proof system, such as bulletproofs or Starks. And really, my personal opinion here is that the issue was not so much that there was a trusted setup, but that people couldn't tell if something had gone wrong. There was no knowledge of the total supply of coins. Okay, We are using a trusted setup. It's a simple trusted setup, assuming that it's been audited well and implemented well. We wouldn't expect things to go wrong with that layer of the application. But we're not able to use the exact format of Powers of Tau. In particular, Powers of Tau gives some elements out in the setup which we do not want people to know. So we would have to run one from scratch if we wanted to run our protocol. Okay, one quick side note, we can aggregate other things as well. And in particular, in the paper, we describe how to aggregate BLS signatures. But for the purpose of this talk, I was talking about snarks. We're not able to aggregate anything which is like multi-round though, or that uses the Fisher-Shamir transform. So for the last part of my talk, I'm just going to be switching topic a little bit, still talking about our work on inner pairing product arguments, but now talking about how they're relevant for privacy solutions, such as the Nightfall application. So these applications are using snarks, and often the most efficient snarks have a one-use only trusted setup. There has been a lot of recent papers on universal snarks, which have many applications per setup approach. And this is something I consider to be better, at least for the following reasons. With a one-time only setup, every single application you run is going to require a new setup, which means that the circuit representing your constraints needs to be got right the very first time. And if there are bugs, you can't fix them. And if there are efficiency improvements, you can't implement them. With a universal setup, however, every application can use the same setup, which gives you sort of more ability to audit things, more ability to check everything's going okay. The circuit representing the application can be edited. So if you make a mistake there, you can fix it. If you find an efficiency improvement, you can fix that as well. So we're able to help implement these universal snarks with a smaller setup. So the ones that are in the literature at the moment, they have very, very large setups. They scale linearly in the size of the circuit. And if we take the example of the Aztec setup that was run recently, they required gigabytes worth of data in order to run this setup. It was for a very large computation, to be clear there. And they also had very high prover time requirements. So if you wanted to participate in the setup, for example, they were allowing you to have 6 hours in order to run that computation. And that's assuming quite a fast computer. You can improve on this just by having smaller circuits. But what we suggest as a potential alternative is using Sonic or Plonk or Marlin with our polynomial commitment scheme. And the benefit here is not totally free. We do have larger proofs, we do have higher verifier time, but our setup would take something that was 32 megabytes down to 50 kilobytes, for example. It's square root size. And that benefit, it also helps with the prover time. Our prover time is going to be smaller, at least when it comes to that part of the snark. But again, not totally free. There is some trade-offs to be made here. This is the table in the paper where we're talking about how we fare in terms of efficiency. You can see that we've included a transparent and a structured version of the efficiency table. This is because we do provide a way to implement the scheme with a transparent setup. However, our verifier time is quite a lot heavier with that. We get square root verifier time. Whereas with a structured setup, we can get that down to logarithmic. We can also support bivariate polynomials, where the efficiency is going to depend on the total number of coefficients, non-zero coefficients that is. And this is something which I don't believe people have managed to do before. So just to wrap up, the 3 takeaways I would give from this talk is that it would be very nice to have precompiles for target group operations in Solidity. We can aggregate snarks proofs with very cheap provers and without having to use pairing cycles. And we can build universal snarks with very cheap prover time. Thank you very much. Stop share.
All right, thanks, Mary. So I think we're actually going into another 5 or 10-minute break. And so this is a good chance for everyone, of course, to catch up on your own emails, but also submit any questions in the Q&A portal. Thanks, everyone. All right, so we'll kick things off in about a minute. Yusuf, I'll ask you to please start your video, and whenever you're ready, you can share your screen and take it away.
Yeah, sure. So, are you able to see my screen? No, you're not. No.
Yes, we can now.
Cool. So should I start?
Yep, sure thing. Go for it.
Yeah, sure. So hi everyone, my name is Yusuf Al-Husni. So I work at EY in the blockchain team, and I'm also a first year PhD student in Grace team at École Polytechnique in INRIA. So today's presentation is going to be about a joint work with Aurore Guillevic, who works at INRIA Nancy. So it is a joint paper titled Optimized and Secure Pairing-Friendly Elliptic Curves Suitable for One-Layer Proof Composition. So just to give some context, we'll be talking about zero-knowledge proofs, and more precisely ZK snarks, and proof composition of those ZK snarks, both from a theoretical point of view and implementation point of view. And then we will be mentioning some applications that might be interested of this work. So a zero-knowledge proof is a proof that is sound, complete, and zero-knowledge, meaning that if the statement is false, then no cheat improver can convince an honest verifier. Complete, meaning that if the statement is true, then an honest verifier will be convinced, and zero-knowledge, meaning that it leaks no private information. So as a subset of those zero-knowledge proofs, we will be talking about ZK snarks. So those argument, which is a relaxed notion of proofs, meaning that the soundness is only computational, complete and zero knowledge, but additionally succinct, meaning that the proof is very short and easy to verify informally. Non-interactive, meaning that there is no necessary interaction between the prover and verifier. And of knowledge, meaning that the verifier will be convinced that the prover knows process and information. So zero knowledge proofs, ZK snarks as a subset, then pre-processing ZK snarks of NP language as a subset, just to establish some notations. So we have an NP program, an undeterministic polynomial program, which is public, with public inputs X and private inputs W. And this public program verifies that F evaluated at X and W is equal to 0. So a ZK snark formally consists of 3 algorithms. So a pre-processing ZK snarks of NP language, setup, prove, and verify. So setup takes the public NP program, some security parameter lambda, and some trapdoor, door, and output some material key. So proving key as in PK and verification key as in VK. The proof algorithm takes the public input and the private input, so XZ, PK, and W, and output some proof that we denote pi. And the verification algorithm takes all the public inputs and the proof pi and outputs a Boolean 0 and Y, whether the NP program is satisfied or not. So the trusted setup can be generated by anyone as long as it is a trustworthy party. The verification, the prover by Alice the prover, and the verification by the verifier. So we said that the key property in those ZK snarks is the S, which stands for succinctness. So informally and honestly generated proof is very short and easy to verify. So there are many definitions of this succinctness, but here we take the one from BCTV, as in the paper of Ben-Sasson, Chizat, Romer, and Vasas, and Virsa. So the proof is constant size with respect to some security parameter, and the verification is also constant with respect to the size of the input. So we've been talking about zero knowledge proofs, zero ZK snarks, pre-processing ZK snarks for NP language. So here is the last subset we will be focusing our presentation on, is pairing-based pre-processing ZK snarks for NP language, or in short, pairing-based ZK snarks as referred to in the literature. So those ZK snarks use some maps, some functions called pairings defined over elliptic curves. So this slide is just to establish some common notation that will be useful in the sequel. So we need some elliptic curve E. So this is the short Weierstrass transform of an elliptic curve defined over a field of Q, a characteristic Q. So of course, the characteristic is different from 2 and 3. So the order of the elliptic curve is equal to Q. So the characteristic plus 1 minus T, with T an integer called Frobenius trace. So it has a prime divisor, so a subgroup of order R. So we will be talking about elliptic curves of complex multiplication. So those that satisfy this equation, 4Q is equal to T squared plus D y squared, same Q, same T. D is the complex multiplication discriminant, or minus D as in conventions, and Y is some integer that satisfies this equation. So small d is the degree of the twist, small k is the embedding degree, meaning that the subgroup order R divides Q to K minus 1. So this slide is just for some notations. We will be recalling them later. So we have two groups, G1 and G2, and we have a pairing that goes from G1 to G2, two groups of order R, to some target group, which is R thought of unity in the kth extension FQK. So yeah, so here we will just give an explicit protocol of those pairing-based ZK snarks. So growth 16 due to growth, to Jens growth. So we have an instance, so the public input A sub I, that satisfies an NP program F. So we have our algorithm set up, prove, and verify. So here we give explicitly the verification key, as we will be focusing on the verification side. So it is a bunch of elements in those groups, G1, G2, and G2. And the proof is 3 elements in an elliptic curve, A, B, and C. So we see that it is constant size with respect to some security parameter lambda. And the verification is equation 1, which is this equation, which is a pairing product equation. So we see that it is constant size with respect to the instance, because we have just Vk sub x that we have to compute, which is related to A sub I, which is the instance. So it is constant. So the proof is constant size, the verification is constant time with respect to the security parameter and to the public inputs. So from now on, we will be focusing on growth 16 as an application of this. So just to motivate this talk, so a blockchain is a decentralized, transparent, immutable paying ledger. So, but those transparent, immutable paying, it results in some problems. So transparent, so it results in some confidentiality problems. Immutability, which means that everything written, once written, cannot be removed. Some scalability problems, and paying fees result in some cost inefficiencies. So ZK snarks are one solution to solve these 3 problems, because the proof is zero knowledge. So we have confidentiality. So the proof, as in growth 16, for instance, is constant size. So we solve also somewhat the scalability problem, and the verification is also constant with respect to the instance, which solves somewhat also the cost problem. So just on Ethereum, for example, for Lambda, which is 110 bits, because they are still using the BN254 curve, a proof is somewhat 254 bytes. So a question is, how much does it cost in space and fees to verify 1,000 proofs, for instance? So the answer is like 1,000 more in space and fees. So another question is, can we aggregate those 1,000 proofs into a single constant size proof? Or can we verify those proofs at the cost of 1 proof, or can we maybe do both? The answer is, since we are talking about ZK snarks for NLP language, then the equation 1, which is this one in this slide, so is also an NP program. So one can generate a proof, a new proof that verifies the correctness of the previous proof, or say many other proofs. So maybe we will have 2 scenarios. One is when we have the number of proofs is not fixed, so we need to aggregate on the fly. Or maybe the number of proofs is fixed, and then maybe we can just aggregate once. So let's see the arithmetic side of things. So how easy and difficult it is to express this equation 1 as an instance of an NP program. So remember that equation 1 is a pairing product check. So it takes place in a kth so in the field FQ2K, so a kth extension of field FQ. And to generate the proof, so we work in the subgroup of order R of the elliptic curve. So Q is the size of the field, R is the subgroup of the curve. So here we have obviously an arithmetic mismatch. So one first attempt to solve this is to choose a curve for which Q is equal to R. So this is unfortunately impossible for pairing-friendly elliptic curves. The second attempt will be to simulate FQ operations via FR operations. So this is possible, but we would introduce a blow-up, an overhead of size log Q with Q a big cryptographic number. So the third attempt, which was introduced in BCTV paper, is to use a cycle of elliptic curve, which means not only one elliptic curve, but maybe two or many. So the idea is we can solve this mismatch arithmetic by requiring the second ZKP system to use another elliptic curve that satisfies some condition in order to solve this arithmetic mismatch. This notion was also relaxed later in the ZKP paper by Bo, Chiza, Paratush, and others. So just to establish some formal definitions, an M chain and an M cycle. So we have M elliptic curves for which the subgroup order of one is equal to the field size of the other one. And if we require the last one to satisfy the same condition with the first one, then it is a cycle. So M chain, M cycles, or two chains, two cycles, if we have only two elliptic curves. So here there have been propositions in the literature. The first one was in the BCTV paper, so namely the curves MNT4 and MNT6. Then there was another proposition that is used today in CODA, MNT4 753, MNT6 753. And then in ZKP paper, there was two chain construction, namely the inner curve BLS 12377 and the outer curve CP6782. So this talk is about a new outer curve that replaced CP6782 while enjoying very efficient implementation. So just to look at why we have all those constructions. So the MNT4, MNT6 is the only construction we know of for the time being that forms a cycle of pairing-friendly elliptic curves. And unfortunately, it is not efficient at 128 security, bit security. So one solution is to find another construction, and the other solution is just to increase parameter. So this was done in CODA, and they increased parameters, but this results in heavy curves. So for the chains, so the inner curve BLS 12377 is somewhat the state of the art with respect to pairing-friendly cryptography because it enjoys all the efficient properties at 128 bit security. So the outer curve, however, CP6782 has some inefficiencies at 128 bit security that we try to solve in this new curve. So just to look at the big picture, so if we are doing pairing-based snarks, we need one single elliptic curve. So this elliptic curve should satisfy two properties. So it has to be pairing-friendly so that we have this efficient map that we will use for verification, and also the subgroup order -1 should be highly two-adic, which means divisible by a high power of 2. So this second property is for efficient FFTs. So it is not a must, but it is very, very important to have. So we can then choose from a wide range of pairing-friendly constructions, such as Barreto-Naing, Barreto-Linscott, Brezing-Weng, KSS, and others. So there have been propositions from BN and BLS12, for instance. If we want to do recursive snarks, then remember we have those two scenarios, two cycles and two chains. So if we want two cycles, then we need two elliptic curves that we have to construct at the same time, because both have to be pairing-friendly, and the subgroup order of one should be equal to the field size of the other, and vice versa. So we need to construct them at the same time. And for efficient FFTs, for proving, we need all the parameters. So R sub 1, R sub 2, Q sub 1, Q sub 2 to be highly two-adic. So the only construction that we know of is MNT4, MNT6. There have been some negative results established in a CCW paper by Chiza and his co-authors. So if we want to do a two-chain, then the key property here is that we are allowed to construct these two elliptic curves in a sequential fashion, meaning that we start by the first curve, namely E sub 1, and then we construct on top of it the second curve. This gives us all the flexibility. We want to construct this inner curve. That's why it resulted in BLS 12377, which is very efficient. The outer curve, however, is should be constructed in a way such as each subgroup order is precisely equal to the field size of this E sub 1 of the inner curve. So the only construction that we know of that from the literature is Cox-Pinch. So this one was used in ZKP that resulted in CP6782 curves. So just to recall those properties we need to check. So these slides are by the way from another presentation that was in a longer format. So maybe we will be skipping a little bit the math details to go to the results. But so in Cox-Pinch algorithm, for this outer curve, we need the Q to be prime power, the Frobenius rate to be relatively prime to Q, so that we have only ordinary elliptic curves. The subgroup order prime R divides Q plus 1 minus T, and the embedded degree is K, and the equation, the complex multiplication equation is satisfied for maybe for small d in order to use that schema algorithm to find the coefficient. So this has to be replaced by just one condition, which is R is fixed and chosen to be prime that divides Q plus 1 minus T and Q2K minus 1. So the Cox-Pinch is very easy to understand. By the way, we need just to find kth root of unity. So Q is congruent to T minus 1 modulo R. So we just require K to divide R minus 1 and minus D to be square in FR. So that T minus 1 is a root of unity, and then we can satisfy the complex multiplication equation by construction. So there are two problems with this with Cox-Pinch. So the ratio is at least 2. So which means that the second elliptic curve, the outer elliptic curve, will be twice as big as the first one, and the parameters of these curves are not expressed in polynomial parameters, which we like to in order to have efficient pairing-based cryptography implementation. So what we did is we replaced this Cox-Pinch algorithm by Breising-Weng method, which is mutatis mutandis taking Cox-Pinch into the polynomial domain. So this solves the first problem, but in our case, we wanted not to find a polynomial R, but to find R exactly. So we had to do some shifting in order to find the polynomial evaluated in the same seed as BLS 12377 equal to the subgroup order we targeted. But then is Q evaluated in this seed is also a prime. Otherwise, we cannot construct the elliptic curve. So as I said, I will be just skipping because of the time, but we can take this to the chat. So our work resulted in a elliptic curve, so that we called BW6761, which has this equation y square xq minus 1, which is defined over field 761 bits. The seed is this one, and we have polynomial parameters of all the parameters. So the results, if we want to compare this work with ZKP CP6, is so the curve is defined over a smaller field by one machine wide 64 bits. So the curve has embedding degree 6 and twist degree 6. So what does this mean? It means that the element in G2 can be factored, can be compressed to 1/6. So G2 as in the proof element and the trusted setup element. So the curve has parameter polynomial expressions allowing fast implementations. We find also a very efficient optimal 8 pairing. And also in the paper, we describe other optimizations such as GLV multiplication on both G1 and also G2, because we fixed the complex multiplication discriminant to be equal to 3. We have very fast subgroup checks rather than just multiplying by the subgroup order. So those are based on endomorphisms. And the curve has also secure hash2 curve and fast hash2 curve for both G1 and G2. So the details are explained in the paper. So here I think I just have maybe a few minutes more. I will just focus on the verification equation. So the verification equation, so the building block is the pairing computation. So in violet is what, so the pairing that we have in ZKC for CP6, and in blue, the pairing that we have for our curve. So it is an 8 pairing. So 8 pairing, so there are two parts. So the first one is what we call the Miller loop, and the last one is what we call a final exponentiation. So the Miller loop has a size. So in CP6, the size is 388. In our case, we have two Miller loops, but both in smaller size, so 64 and 182, I guess. And the multi-exponentiation, so this is a classical trick to do the final exponentiation. Easy part, hard part. The easy part is the same, but the hard part, since we have polynomial constructions, then we could find a very efficient algorithm to do this very quickly. So from a theoretical point of view, if we compare CP6 to BW6, so the total number of operations is almost 5 times less, and in a field that is smaller by one machine word. So we implemented this first in C++, but then we implemented it in Rust to have a more like apples to apples comparison. So there is a pull request that has been merged by Pratyush on ZKC master. We see that it was 15 times faster to compute a pairing and 29 times faster to verify a Gauss-Sex import, because in Gauss-Sex, in this pairing product equation, we can factor the final exponentiation. So we see a huge gap between the theory and practice, but just because in the ZKC implementation, they use a fine coordinate for pairings, which is, by the way, advised to in the very specific case of CP6. But this has to come with fast implementation of the inverse in the cubic tower field. But that wasn't implemented at this point. So some application that might be interested of this work. So of course, ZKC. So kudos to the folks behind ZKC. So we can replace the CP6 curve by BW6 curve. So this has already been done in the ZKC repo, pull request merge. So Celo is are using ZKC system to batch BLS signature. So we can also substitute the curves. Filecoin. So Ariel mentioned some times ago that they were considering circuit splitting. And last, EY Midnight ZVM. So that was introduced earlier by Michael. So we can use this curve also to have private smart contracts on Ethereum. And I think that's it for me. I will be sharing the slides, so links are here. And for more details, yeah, we can take this to the chat. So thank you.
All right, great. Thanks, Yusuf. Really appreciate it. Pratyush is going to be up next, and just an FYI, fortunately, this session will be leading into our final 5-minute break. So I know we went over a couple minutes. If you, Pratyush, want to go over a couple minutes, that should be fine. So thanks, Yusuf.
Awesome. Hi, everyone. Hopefully I can try to share my screen now. Okay. Share. And okay, can everybody see my screen? Okay.
Yes, we can.
Okay, awesome. Okay, hi everyone. Thanks for having me. I'm Pratyush, and I'll be talking about ZKC, which is a library for developing with ZK snarks, by which I mean developing applications with ZK snarks as well as developing ZK snarks themselves. Yeah, so this library was originally developed as part of the ZKC paper, which constructs these private smart contracts and with these excellent co-authors. But in this talk, I'll be focusing more on the library itself instead of the paper. Okay, so let's get started. So let's say you want to develop a ZK snark application, right? So something like Zcash or Coda or Nightfall or Celo, or any one of these applications, right? so aside from the task of figuring out what business logic you need, you also have to figure out what you need to do with zero knowledge proofs inside your application, right? But once you start diving in, what you'll probably find is that there's a deep ocean of components that you need to figure out. For example, you need to choose which proof system that you want to use in your application. You need to figure out which elliptic curves that you will need to use in your application, along with some figuring out what arithmetic for the finite field FFTs you'll need. And finally, once you've made these choices, you need to actually go ahead and implement the business logic for your application inside the SNARK itself in what's called constraints, which are used inside SNARKs, right? And so if this seems like a lot of knowledge or not a lot of information that you need to know for developing applications, it is, right? You need to figure out how to implement optimized arithmetic for your elliptic curves. You need to figure out what kind of security properties you need from the various SNARK constructions that are out there. There's so many nowadays. You need to figure out how to actually implement your program efficiently inside the constraint programming model that is used inside SNARKs, as well as you have to make sure that what you do implement is actually secure. And finally, after all that, you need to integrate all of these components into a single package. And this can cause issues because you're composing relatively advanced and tricky cryptographic protocols. So you have to be careful in that portion as well. To top it all off, there's new techniques for all of these components every few months. So keeping up to date with these new techniques for efficiency and security can be tricky, right? So what we want to do in ZKC is to try to minimize the effort in sort of integrating or making a choice in this large decision space to make it simpler to develop applications and to keep your applications up to date and efficient and secure. Okay, so yeah, I'll be talking about three, I guess, 4 properties of ZKC that we want ZKC to have. Right? And I'll be talking about the 3 domains that I mentioned, so elliptic curves, proof systems, and constraints. So from an ergonomics and extensibility perspective, you want it to be the case that if you're developing an application that requires a proof system, which itself requires some fancy elliptic curve, it should be easy to extend the infrastructure in ZKC to implement this elliptic curve in a performant manner. Your proof systems that you develop, which a new one comes on the market, you want to change to that, it should be easy to implement this proof system while taking advantage of the optimized components that are already used by the existing ZKC ecosystem. And finally, in implementing constraints, we should be able to get constraints that are, to be able to program constraints in such a way that it's as close to programming native code as possible, right? So it should be very ergonomic. You shouldn't have to reason about things like the proof system or the choice of curve and so on and so forth. And this brings me to the next point of modularity. What we want from our library for elliptic curves, for example, is that we should have a generic implementation of elliptic curve arithmetic. So when you implement a new curve, you don't have to implement, the point addition and point doubling and so on and so forth. And your proof system should be generic with elliptic curves so they can easily swap in and out curves as you need. And similarly for your constraints, they should be independent of the proof system in some sense. You should be able to swap in and out proof systems according to your requirements. Now, both of these extensibility, ergonomics, and modularity requirements should not come at the expense of performance, right? What we want is that our generic implementation of elliptic curves should match or at least be somewhat close to optimized handcrafted assembly implementations of curve-specific arithmetic, right? And similarly for proof systems, we want it to be the case that our generic implementation that uses generic components is actually very close in performance to specialized implementations that leverage the structure of the proof system very closely. And similarly for constraints, what we want is that our ergonomic, close to native programming constraints should be very similar to a very hand-optimized raw constraint writing experience. Okay, and finally, from a security perspective, we want a sort of boatload of requirements. One crucial, I guess one important goal, especially when you're dealing with components that are important for security, is that you want memory safety, because that just cuts down your attack surface. We want to take advantage of the modularity and the generic aspect of our library to be able to reduce the number of lines of code that need auditing. We want to have APIs that directly enforce correctness without relying, without allowing users foot guns to shoot themselves with. And finally, we also want, can't quite see the bottom of my slide, but okay. Yeah, we can move on. Yeah, so what we try to do to achieve all these goals is we construct libzexi, which is a series of libraries that are composed into one tightly knit framework. And we develop libraries for generic arithmetic, as well as in concrete instantiations of this elliptic arithmetic for various curves. We have a library for polynomial arithmetic, and a library for generically developing constraint systems. On top of all of this, we build a variety of proof systems, such as Groth16, GM17, as well as the inner pairing product proof system that Mary mentioned earlier. And we have implementations in the ecosystem also of the Marlin universal setup proof system. And on top of all of these, to take advantage and to actually use these proof systems, we have some libraries that enable easy programming with in the constraint system model. Right? So we have a library for common primitives, such as hash functions, Merkle trees, along with their constraints, as well as a library of gadgets for things like elliptic curves, finite fields, and such, which allow you to use these objects inside your SNARK. Okay, so in this talk, I'll be focusing a bit on sort of how our generic the interfaces between these components allow us to achieve the properties that I mentioned on a couple of slides ago. The extensibility, the ergonomics, the modularity, the performance, all of these properties. I'll focus on two particular interfaces that allow us to achieve these properties. Okay, and I'll do this by focusing on some components in this large stack. So I'll focus on the curve infrastructure, and then I'll talk about how our Groth16 implementation takes advantage of our generic curve infrastructure. And finally, I'll talk about our constraint system infrastructure. Okay, so let's get started by looking at our elliptic curve infrastructure. So yeah, so all SNARKs that we know of today require, as you might have seen over the course of today, require what's called finite field arithmetic, as well as arithmetic over elliptic curves that are defined over these finite fields, right? And so there's a lot of choices of elliptic curves that you could make, and different proof systems, such as Groth16 versus Marlin versus something like bullet proofs, all have different requirements on the choice of curve and field that you would want. So if you want, while developing a library for these elliptic curves, what you want is the library to be allow easy implementation of new fields and new curves, while ensuring that the performance of these curves that you do implement is on par with the handcrafted implementations. Right? Okay, so let's see how we achieve this in Zexi. So I'll be going with an example of implementing the Brett and Eric 254-bit curve, which is used in Ethereum. It was also used in Zcash a while back. I'll show how our infrastructure in Zexi allows us to implement this curve in very few lines of code. So, okay, so that's some background. To implement the curve, what you need is at least to know the curve equation. In this case, it's some ax plus b. There are some a and b constants specific to Bn and Bn254. And so to implement the curve, we have to implement the underlying fields. I won't talk about that here, but rest assured, it's not a lot of code either. You have to specify, now coming to the curve itself, you have to specify the constants that you need to implement the curve, so a and b. So this is done in like 10 lines of code here. And you need to specify also sort of information about the group generated by these curves, so the cofactor of the curve, as well as the generator of the curve. Right, and so this is all the only information that you need to now implement Bn254G1. Now you can go ahead and take the resulting struct and use it in your code wherever you please, and it'll enjoy efficient arithmetic. Right? And what we do in Zexi is we take advantage of this simplicity and implementing curves to implement a lot of curves that different projects use. For example, we have implementations of the BLS 12381 curve, which is used by Zcash, as well as Algorand, Dfinity, and other projects in the system, in the ecosystem. We have the implementation of the BN254 curve very recently, thanks to Yusuf. We have implementations of the BLS curve 377 curve, along with CP6 curve from ZKs, as well as, again, thanks to Yusuf, we have the implementation of the BW6 curve. So this allows, as Yusuf noted, this sort of one-step recursive verification of SNARK proofs. And to support these cycles of curves, we have also implementations of the MNT cycles that Yusuf mentioned. And yeah, these are used by various projects, again, in the ecosystem. And the nice thing is that all of these curves, they, for example, share the same underlying field arithmetic. They share the same underlying group arithmetic, where you don't have to re-implement it separately for each of these curves. And this allows us to reduce the amount of code that you need to audit if you want to use the library. And one further advantage of this is that now, if you have a project that interacts with multiple of these ecosystems, with, like, for example, you want some sort of bridge between Zcash and Ethereum, then you can use our library to directly take advantage of, or to be able to work with the curves that these projects use. So you don't have to pull in Zcash's Bellman and then BN254 from a different project and somehow integrate them. You can just use ZKs and you'll have both of these curves available for you directly. Aside from these, we also have other curves, such as the twisted Edwards curves, which are used for Pedersen hashes and so on and so forth, all implemented generically again in ZKs. Okay, so this is very nice. So we have a large set of curves that are used by various projects. The question is how does the performance of these curves compare to the specialized implementations, right? So so let's take a look at the performance of the BLS12 curve, 381 curve, on some metrics such as G1 additions, G1 doublings, pairings, and multiplications in the base field. So the baseline that we'll be looking at is the implementation in Bellman, which is an entirely safe implementation, but is specialized to the BLS12 381 curve. And we'll be looking at also a very, very optimized library called MCL, which uses tricks like dynamic code generation and specialized assembly to improve performance, right? And sort of these are the two ends of the spectrum. One is completely safe code, and one is relatively it's using possibly dangerous tricks like assembly implementations and dynamic code generation. So let's see where ZK lies in between these two extremes. So first we'll be talking about our safe implementation, which uses no assembly language. This is all in safe Rust. There is no unsafe code anywhere. So as you can see, the performance is very close to the the specialized implementation in Bellman. So we're off only by maybe a couple of percentage points. However, we do also have an assembly implementation in ZK, thanks to a recent PR from a community member. And this greatly improves the performance of field multiplications and group additions and so on and so forth. And we see that we get actually very close in various respects. And sometimes we even beat the performance of the MCL library. So yeah, because you can see the field multiplication is very close, but and the group operations are almost there. There's a difference, the discrepancy in pairings, and probably investigate why that's the case. But anyway, the pairings are usually not the critical bottleneck in the system. Okay. Yeah, so just wanted to point out from this slide that we have both safe and unsafe, like assembly using implementations, and these achieve performance that match sort of the state of the art in the ecosystem. Okay. So that was it about the elliptic curve infrastructure. Let's see how we can use these infrastructures to develop proof systems inside ZK. So we're focusing on the Groth16 proof system. So as I said earlier, the SNARK landscape is evolving quickly. Every few months, you come up with a new proof system or an optimization to an existing one. So what you want to be able to do is iterate. If you want your application to take advantage of these advances, you want to be able to quickly switch out your old proof system for a new, more optimized implementation or new optimized scheme, right? And you also want your proof system to be able to take advantage of advances or changes in the status quo regarding the underlying elliptic curves and finite fields. So what we want is to have modularity, so we can switch between these curve systems easily. We implement new proof systems easily. We want to go from pseudocode to code very easily. And finally, we want the performance to be competitive with implementations that are specialized for specific curves and for specific proof systems, right? Okay. So from the ease of implementation perspective, what I have here is some diagram of the Groth16 verifier. On the left-hand side is the pseudocode from the paper, and on the right-hand side is its implementation in Zexy. As you can see, the implementation almost exactly matches what's written in the pseudocode. There's almost no difference there. And so the advantage of this is that it allows you to easily implement a protocol by just looking at the paper, and you can directly use the Zexy APIs very easily to implement it. But yeah, and this also improves the auditability of the code. If you have an auditor who's looking at your implementation, they can look at the paper, see them, and match it up with what's implemented in the library. So this allows people who are not as experienced with these relatively complex protocols to become more proficient, more knowledgeable in these protocols, and sort of expands the knowledge base of people who are able to work with snarks and work on snarks. Okay, so hopefully I made it clear that we have this nice ease of implementation property. From a modularity perspective, what we want, as I said, we want to be able to switch between curves very easily, and our implementation is entirely generic over the choice of elliptic curve. So to switch from, for example, the BLS 12381 curve to the BW6 curve, all you have to do is switch one parameter in the generic implementation. And similarly, for switching between proof systems, it's again super easy. We have a sort of common API that all of the proof systems implement, and you just switch out which proof system you're actually using. And you can combine both of these to search proof systems and curves at the same time, whatever you want. Okay, I won't focus on the performance here in the interest of time, but the performance matches, again, the implementations, for example, in Bellman, as well as in lib snark. Okay. All right, so you covered a lot. We're coming to the end of the presentation, and now I'll be talking about how our R1CS interface, our R1CS gadgets library can be entirely generic in terms of the underlying proof system. It doesn't reason about it at all, and what kind of ergonomics properties we achieve, right? Okay, so programming for snarks is sort of traditionally been thought to be a relatively painful activity because, just look at this equation there, right? There's some AI times WI in a product with some BI, WI, and it looks all very super messy, right? And yeah, directly programming these constraints would actually be painful. So what you want to try to do is to have some sort of high-level approach to programming in this constraint system model, right? And have this high-level programming sort of compiled down to R1CS in the backend. And then you can plug this R1CS into your proof system of choice, right? But the problem is that for these high-level approaches, balancing performance and ergonomics is tricky, right? Because on the one hand, you want to have like a high-level implementation that reads very easily, but you're worried about leaving some performance on the table when you're moving to this high-level implementation, right? So what we want to do in terms of in Zexy is to sort of balance these requirements. From an ergonomics perspective, we want it to be the case that when you're writing code that is used inside a snark, it should be very similar to the code outside a snark, right? So it should be very, very similar to native code. Next, you want to be able to reuse components. So, if I implement a collision-resistant hash function like the Pedersen one, you shouldn't have to re-implement that. You should be able to take my implementation and plug it directly into your circuit and use it as is. And finally, we want the performance of this ergonomic and reusable implementation to match very closely the performance of a specialized handcrafted constraint system where you go in and manually fiddle with the constraints, for example. Okay, so let's see how we can achieve this. So from the ergonomics perspective, what we have currently in Zexy is sort of fairly ugly and maybe unreadable implementation of some logic. So for example, on the top, we have an implementation of some arithmetic for a quadratic extension, right? And on the bottom, we have an implementation of that same arithmetic, but expressed in terms of constraints, right? So this is what your constraint system would take as input, right? And so it's kind of difficult right now to see the mapping between the native code and the old constraint code. Right? So what I've been trying to do over the last couple of weeks is try to really improve the ergonomics of writing the constraint code. And what I managed to achieve is an API which is basically the same as the native code. So on the left, now you have your native code. On the right, you have the constraint code. And as you can see, they look basically exactly the same. There's almost no difference between the two, except for some reference taking. And sort of this is the goal that I have for the rest of the library. This is a PR that's in progress on the repo. And over the next week or so, I hope to finish it off. And with the end goal being that writing your constraint code should be very similar to writing your native code. Now, this has benefits not only for people who are directly writing constraints inside Zexy, but also for people who are, for example, developing high-level programming libraries on top of Zexy. So what I mean by this is, for example, if you have Socrates, and what you can do is, instead of compiling down to something which looks like what's on the bottom here, right? Your compiler can output stuff which looks like what's on the right here. And the idea being that now the output of your compiler from your high-level language to what Zexy understands could be much cleaner and much more easy to audit. So you can debug your compiler also easily. Okay. So yeah, so that's from the ergonomics perspective. What we want to do is also take advantage of,
Pratish, very, very sorry to have to cut you off, but I think we've got to jump right into Ariel's presentation. So yeah, sorry about that. Do you want to just give maybe some quick closing comments?
Okay, yeah, so I was about to finish off, but yeah, basically we have an implementation of all of the components. So this is the library again. So there's been a lot of excellent community contributors who've contributed a lot of what I mentioned in the previous slides. If you want to contribute, please get in touch. The email is here and the link is, my email is here and the link is there. And yeah, so these are also the links to the various projects that I mentioned in the slides. Sorry for going over time. Okay, yeah, that's it.
No problem. Thank you.
Thank you.
All right, I'll just put this up for 1 minute while Ariel is pulling up his information. So Ariel, if you have your presentation, feel free to share your screen whenever you're ready.
Okay. Okay. So this is about a recent, mainly about a recent paper called Plookup that I wrote with Zach Williamson from Aztec. So sort of the motivation for our Plookup work is that snarks are easy prey for in a world of nasty binary functions. And what this means is that when you're writing some sort of program inside a snark, you need to express that program in terms of native field operations, typically in a large prime field. But say you're looking at some function, some hash function that has operations like bitwise XOR. So you have you're thinking of your inputs as elements in this native field, but you want to do a native XOR, bitwise XOR between them. You also want to check that they say, if it's 8-bit string XOR, they really correspond to an 8-bit string, and then that C is equal to the bitwise XOR of A and B. When you write the field element as you represent it in bits. So sort of the standard way of doing this is to sort of put a lot of variables in your constraint system, and one for representing each bit of A, B, and C, and now do these quadratic bitwise constraints. So this would cost you, say, 25 to 32 R1CS constraints. And now the problem with this 25 to 32 is that it's not something you pay once. It's a multiplicative factor, so that you pay. So think of doing a SHA or Blake hash. So right, the whole, if you look at the description, it's right. Every instruction sort of is one of these operations. So basically, when you're if you try to write your hash function as like a sequence of 8-bit operations, you're going to pay this 30 factor for every operation when you write it inside the snark. So this has led to one rich line of investigation in the last few years of keeping snarks in friendly neighborhoods. This is research on how can we construct good hash functions, good ciphers, such that all the or almost all the operations are native field operations. So for example, this in this line of research, we've got the MIMC, Poseidon, and rescue hash functions. Right, and the idea is, okay, maybe we can, whenever we need a hash function or a cipher, we'll use something in this neighborhood. And what we try to do in this work, and this is it's similar to a previous work called ARIA, is let's say no, we do want, right, especially if, for maybe argument's sake, right, if we want snarks to get out of the playground and in a sense be usable by everybody, IoT, you don't want to tell your consumer or your another engineer who's not aware of this world that, oh no, you can't use SHA or AES, you have to use this thing that we came up with. So the idea is, instead of expressing the operations as constraints in your native field, which inevitably will be expensive when your field is prime and your operations are bitwise, simply sort of pre-compute a lookup table. For example, a lookup table of all field elements triples ABC, so that when you look at their bit representations, they're all 8-bit elements, and C is equal to the XOR of A and B. And then the idea is that maybe you can somehow just check that this tuple ABC is in your pre-computed table, rather than actually expressing the XOR bitwise XOR logic in your big prime field. And the idea is that you can sort of do this in a way that when you do enough of these lookups, roughly the number of lookups should be as large as the table. That's when it starts to pay off. When you do enough, then these lookup checks have an amortized constraint of 1. Amortized cost of 1 constraint per XOR, instead of this 25 to 30, say. So that's the motivation of Plookup, and let me give you a sort of an explanation of how this protocol works. So this is going to be a simplified protocol compared to that of the paper with slightly worse efficiency. So the first thing I need to introduce you to this basic tool that we can call the multi-set check. What is the multi-set check? It's say I'm giving you two like vectors of field elements, and I ask, are they equal? It's multi-sets, meaning that you know, up to some reordering, they contain the same elements, also when counting repetitions. And a simple idea that was used in previous works of, I think, various works of Groth, for example, this Bear Groth work that we took inspiration from, is that a simple trick is that you can reduce this multi-set check into a sort of a single randomized product. And so how do you do this? You choose some random gamma in your field. And now, so right, if I have, right, if the A's and B's could be different, but their products could still be the same. Say if the A's are 1, 1, 1, and the B's are half 1, 2. But what's easy to see from the Schwarz-Zipf lemma is that if they're not the same multiset, if you choose some random gamma and now compare the products shifted by this gamma, then with very high probability, if they're different as multisets, the products will be different. And this core contribution of the Planck paper is so okay. How can I actually do this inside a SNARK? This product check and the core contribution of Planck is a really efficient and simple way to do. So say you have two polynomial commitments to two vectors, you can do this product check very efficiently. Okay, so let me try to give you a small explanation, a short explanation of how lookup works. So say, again, our setting is sort of, we have some vector that we think of as the witness. We have some other vector that we think of as the table. And we want to prove that F is contained in T, meaning that every value just in the set, not multi-set sense, meaning that every value in F that appears in F also appears in T. And just a tiny remark, right? That we were talking about tables of tuples, but it's easy to go from the tuple case to the single element case by sort of random combinations. Right. Okay. Oops. All right, so let me give you again just a simple example of the simplified, less efficient version of the lookup protocol. So say, for example, our witness was 311 and our table was 134. So right, in this case, our claim is true, like the values of F are contained in the values of T. And so how will we prove this? So the prover will commit to a sorted version of F union T. And here I'm sort of switching between multi-sets and sets here in the multi-set sense. So concretely, if this is F and this is T, then S will be 1, 1, 1, 3, 3, 4, right? That's the union of F and T sorted with all the repetitions. And now the prover will show that as a multi-set, like S is indeed equal to F union T. So how will he do this? Exactly with this multi-set check that I mentioned. All right, so now we know that S is they're equal as multi-sets, right? But that doesn't tell us so far that the values of f are contained in T, right? That doesn't say that at all. So the next step is to look at the difference multiset of S. So, right, so we just look at each two consecutive elements and look at their difference. So, right, if this, for example, it will be S, so this will be, right, 1 minus 1 is 0, 1 minus 1 again is 0, 3 minus 1 is 2, we'll get 0, 0, 2, 0, 1. And similarly, we'll look at the difference multiset of our table. So if the table is 1, 3, 4, it will be 2, 1. Right, so what we see is, right, that whenever there's a repetition, we just get 0. And since both S and T are sorted, when it's in U, when we're switching element, then the difference in S and T should be the same difference. So what follows is that the claim is true if and only if is multisets S prime is equal to T prime union as many zeros as like the size of S minus the size of T. So that's maybe a little to digest. I'll just, so how does this compare to the paper? So basically, right, if our basic unit of cost is this multiset check, right, we did here 2 multiset checks between S and F union T, and then between the different sets. And what we show in the paper is if you look at what randomized different sets, you can actually combine these 2 checks into one multiset check. Okay, so that was maybe a bit fast. I'd be happy to answer questions, but I'd like to finish by mentioning, so I'm really trying to get it easy to use the Planck proving system. So you're welcome to go to this URL and get a easy web interface for using Planck. Let me just show this to you for 15 seconds, if I'm not over time. Right, so this is sort of what it looks like. You can create a new proving system. You can then put in provers and verify. It's a little different from R1CS, but you have, like, for example, the basic, addition constraint, basic multiplication constraint. And yeah, so I encourage you to give this a shot. And yeah, I'll end there. So thank you.
All right. Sounds good. Thanks, Ariel. Appreciate it.
Sure.
So I think we've got a few minutes until the next session, which is with Dan Brownstein. That is the Starkware presentation. But maybe we can treat this as our 2 or 3 minute break. And if anyone has specific questions, feel free to continue to submit them through the Q&A portal. But for now, we'll take about 2 minutes until Dan's ready. And then Dan, whenever you're ready, you can share your video, share your screen, and just kick things off. Thanks, everyone.
Okay. Hi, everyone. I'm Dan from Stalker. Can you hear me? Let's see.
Yes, we can.
Let's share the presentation. Okay, great. So now it should be there. Okay, so I'm Dan from Stalker. I was part of the eStart project. It's an open source code developed here in Stalker. We heard a lot about the snarks. I'm gonna talk about a different kind of beast, about snarks. So on July 2018, we received a substantial 2 years grant from the Ethereum Foundation. I think at the time it was the largest grant given by them. And we had to select the Stark-friendly hash function and release an open source efficient Stark system for it. In this talk, I will talk a little bit about Starks, the Stark-friendly hash function project, and if we'll have enough time, I'll briefly mention what else we do in Stark. Well, I know it's the last talk, I'll try to keep in time. So a proof system is considered to be Stark if it is scalable. And by scalable, it means that for computation that lasts T cycles, in order to generate proof, it takes roughly T cycles. It is wildly linear in T. And it is verified much faster than that, exponentially faster. And here you can see a benchmark of our open source project. So this is the prover time in seconds and the verification time in milliseconds. And this is for proving this number of hash invocations. So for example, proving the computational integrity of 100K rescue hash invocation, rescue is the chosen hash function. It takes less than 10 seconds to generate the proofs and takes less than 3 milliseconds to verify. And this is really, really fast. So that was scalability. It's also a transparent system, meaning that all verifier messages are random points. There is no trusted setup, not per application, not even a universal trusted setup as we heard in previous talks. There is just no trusted setup. It's really a great thing to have in your proof system. It is an argument of knowledge, meaning that proof can only be generated by party knowing private inputs, not just their existence. Basically means that there is an algorithm that can extract this private output, an efficient algorithm. And there is no public key cryptography involved in the Stark protocol, only very lean cryptography, basically collision resistant hash functions. So it is post-quantum secure. It's really fast, as I mentioned before, and it's based on the reliable trust assumption. So these are the properties of a Stark system. And let's see what's going on inside such a system. So we start with a proof of statement, something along this line. I know a value which satisfies an equation, or I ran this program and I know a secret value X which outputs some value. And an honest prover actually performed this computation, so there is an execution trace. And looking ahead, you know that there are going to be some constraint hiding different sales values. For example, if we look at this line of the code, we know that each value of B value is going to be equal to A cell plus 1. Or if we look at this line, that each A, the next A equals to square of previous B. And of course, there is a constraint about boundary constraint about the output itself. Next, there is a series of reductions. The constraints are expressed as polynomial composed over the trace cells, meaning that we can think of each column of the execution trace as evaluation of some polynomial. So we have the values and we can interpolate them. So we get coefficients, we get the polynomials, and then we can state the same statement as polynomial constraints. For example, each value of B equals to A plus 1 would be in a polynomial constraint something like this, where FA is the polynomial of the A column. And this should hold over a domain. For example, in this domain, it's going to be the trace evaluation domain. Here it's represented as a different power of G, where G is a generator of a multiplicative group of the order of the trace length. Okay, intuitively, we can see where scalability kicks in, right? Because the number of constraints does not correspond to the length of the computation. You have only one constraint for the whole trace. Next, we represent each polynomial constraint as a rational function. We divide it by this polynomial, which vanishes on the domain where the constraint should hold. And since these GI values are actually roots of the polynomial constraint, we know that the denominator should divide the polynomial constraint. So we know that C is not just a rational function, it's actually going to be a polynomial of some bounded degree. And this is exactly what the algorithm is doing next. We do a low degree testing, and we verify that the degree of this rational function is bounded. And if the prover was honest, so it should be the case, and the verifier will accept such a proof. Otherwise, the verifier will reject this proof. Okay. So the reduction between a statement and a rational function, such that the statement is a true statement if and only if the rational function is of a bounded degree. This is the arithmetization part of the protocol. It's just like R1CS. We use algebraic intermediate representation. And the for low degree testing, we use a Fry protocol, which stands for Fast Reed-Solomon Interactive Oracle Proof of Proximity. We'll talk later a bit more about Reed-Solomon maybe. Okay. So there are many parts here, and if we look at the implementation, there are many components in such a system, and what we did in the eStar project, we implemented each component in a way that it is easy to replace them, and you can change the implementation if you wish to something different. Let me explain it a bit better. So the elements in the trace are from a finite field. So we have a finite field implementation, and a finite field in each Stark is the native field of rescue, which is 62-bit long. For standards of the Stark protocol, we need a larger field, so we also implemented an extension field. Everything in Starks involves polynomials, and as I mentioned before, we think of the trace as an evaluation of polynomials, so we can move from evaluation to coefficient and back to evaluation. So we have FFT and IFFT, first Fourier transform in the inverse. We have low degree extension, which is basically evaluating these polynomials on a larger domain. We need this for security as well. So the low degree extension is in fact just the Reed-Solomon code of the trace. This is why the low degree testing is checking for proximity of a code road. So we see if the function is a code road in the code. We have a hash function. We use a Blake 2S, and we use it to implement Merkle trees and commitment scheme on them. We have a hash chain. The hash chain is just a fiat Shamir heuristic. It simulates the interaction between the prover and the verifier, so the system is not interactive. And the way that we implemented all of these blocks is that you can replace them. For example, you can write your own IFFT or FFT, and then you can have even faster call. Or as I mentioned, we use for the underlying hash function Blake 2S, so you can plug in Blake 3, for example, and again, you can even faster, better prover. That's one thing. Another thing is that you can do with this code as an open source code whatever you want. So I mentioned the arithmetization part, which is going from the statement to this rational function. But if you want to write provable for a different functionality, so all you have to do is just rewriting this part of the code. You don't have to do anything with the heavy machinery of the low degree testing and the rest of the protocol. Okay, what I mean is that there is a separation between the protocol, the prover, and the verifier from the statement. Specifically, the statement that we implemented in this project, in the East Start project, was the following statement. It's a hash chain statement. And the prover knows some private inputs, such that invoking the hash function over and over again on these inputs yield some outputs, and the length of the computation, the number of private inputs and the outputs are public, and the inputs themselves are private. And what we did in its start, the hash function is the rescue hash function. Okay, so let me tell you a bit more about the rescue function, or first the process of selecting such a function. So as I mentioned before, it was a 2 years project, started in July 2018. We had to select the start-friendly hash function. And we did a thorough process to make sure that we pick the right hash function, considering the tight schedule. 2 years is definitely not enough time to pick such a primitive. We did our best. At all phases, we have experts in their respective fields doing specific parts. So it started by collecting new start-friendly hash candidates. Even before we started this project, Mimsy was already out there, and gMimsy appeared independently to us. Since the start, complexity of standard hash functions like SHA-2 or 3 is very large, we needed to collect new constructions, and we had contracted 2 teams. One team came with the marvelous family of ciphers, in which you have Jervis and Vision for binary fields, and Pepper and Rescue, which was the hash that we chosen over prime field. The other family of ciphers was the hardest Mimsy family, in which you have Stargate and Poseidon over binary and prime fields. The next phase, we contracted the Cryptonex security company to perform algebraic cryptanalysis. Later, the next phase included several points. First, we had to fix specific parameters to all the constructions in a manner that we can compare them to each other, because they are coming from different families, and we needed a way to compare them in order to choose one. In November 19, we had a start-friendly hash selection committee. It was led by Professor Anne Cantor. Based on the committee reports, we knew that Rescue was a good candidate, but still other tests had to be done. So we had another round of algebraic cryptanalysis, again done by Cryptonex security. And then we have cryptanalytic efforts by expert targeted specifically at Rescue. This was done by a crypto solution. Okay. During the same period of time, we also published, deployed on Ethereum actually, a set of contracts which rewarded the first finder of collision to these candidates. We had just public challenge. The challenges covered several security levels, from 45 bits of security to 256 bits of security. None of the higher level bits of security were broken. Few of the 45-bit security challenges have been broken, but none of the higher. By higher, I mean 80 and above. Okay, so now you know how we chose the Rescue. I'll describe Rescue function itself. So Rescue hash function is Rescue actually is a family of ciphers, and the Rescue hash function is a sponge construction based on SPN, substitution permutation network. It manipulates a state of 12 field elements. The forced 8 field elements are the input, 2 inputs, 4 and 4. We then add a constant value to each of the 12 elements, and then we apply the round permutation 10 times, so we have 10 rounds. And the state of, after applying the 10th round, the first 4 filled elements out of it are going to be the output. So this is a high level of the rescue hash function. If you looked into each round, so each round consists of 2 steps. Each step consists of an S box. In the first step, it's taking the 3rd root of each element of the 12 elements in the state. In the second step is cubing each element. Then it is followed by multiplying by an MDS matrix, maximum distance separable matrix, which mixes elements together. At the end of each step, we add a subkey or a constant to each of the elements. Okay, so that concludes the eStark part of the talk. Again, it was a 2 years project. We had to select a Stark-friendly hash function, and we chose rescue, and then we had to implement efficient Stark prover. And I hope I'll convince you that the prover that we implemented, and it is given as an open source, is very efficient. Just to remind, proving a 100K invocation of the hash function takes less than 10 seconds to prove, and it is verified in less than 3 milliseconds, which is, at least for proving time, from what I know, is by far the fastest prover out there. So I'll briefly mention other stuff we do at Starkware. Starkware, okay, we just talked about eStark, which is self-service. You can do whatever you want with it, from writing even more efficient prover or just prove different kind of statements. We have Vidu. Vidu is a Stark-based verifiable delay function, a VDF function, which emits randomness, and not just randomness. It's trustless and unbiasable randomness over mainnet. We also have StarkX. This is our scalability engine. It supports both fungible and non-fungible tokens, ERC20 and 721. What it does, it processes batches of trades off-chain. It then produces a Stark proof attesting to the validity of each batch, and submits the proof to be verified on-chain. We demonstrated batches of 64K transactions, which means about 9K TPS. Again, very fast. We have tailor-made adaptations for Diversify, which is a non-custodial cryptocurrency decentralized exchange. We have one for Mutable, which is a blockchain gaming company, the creators of a gun on chain. And we also demonstrated how entire subreddit the size of a Fortnite PR, it's about 1.3 million users, could be brought onto mainnet. The focus there was not on TPS, it was on not choking the network. And actually, when we did that, we used about 2.5% of the network, that's all. And we paid below average block gas price, about 30% below. Each transaction cost 600 gas. Okay, that's all. If you have any question or you want to contact us, you can do that. You're more than welcome. I'll just say that the repository for the open source code is here, and just mention that this is still pre-audit. And the README file and thorough documentation will be added in the coming weeks. So thank you very much, guys.
All right. Thanks, Dan.
Sure.
Well, hello again, everybody. Thank you for making it all the way through this fantastic event. I want to say again, thank you to all of our speakers. When I started my very first job out of college, one of the things that they told me at the beginning was, if you want to do well here, you're going to need to be comfortable with your own incompetence. You're going to need to get comfortable with the fact that you work with people that are way smarter than you. And I think I've gotten really comfortable with that because the team that we have here and the assembled experts that we brought together today are so far beyond my own skill set. It's amazing. And I could not be more kind of proud that we are able to facilitate and contribute at this level to the community. That being said, I want to give out a few shout outs, some very specific thank yous to our speakers. So let me do that. 1 second here, make sure I do it properly again this time. So obviously, Mr. Connor, fantastic. Jacob Eberhardt from the University of Berlin, we really appreciate your participation. Mary Maller, we love you. We appreciate your contribution. We are delighted that you're at the Ethereum Foundation, even though it kind of broke our hearts that you decided not to come and work at EY. Youssef, thank you so much. Pratyush Mishra from UC Berkeley, thank you very much. Ariel Gabazon from Aztec and Dan Brownstein from Starkware. We enormously appreciate the contribution that you have made to our conversation today. I want to just recap for 2 seconds a couple of the key repositories, the Nightlight repository. And in fact, generally the stuff that you'll see in the EY blockchain repository and GitHub is all public domain and open source, right? And that includes our deep dive materials, as well as I'd like to point you to the baseline repository, which is also on GitHub. That's kind of where a lot of the work that we're doing is coming together to have private transfers, regulatory compliance, private business logic, and other tools in a single set of infrastructure that allows you to truly build enterprise-friendly, regulator-friendly, privacy-centric business applications. And then with that, I want to do a final thank you to Marika Klein-Smith, who is our global marketing leader and who has done an amazing job organizing these, Eli Wolfson, John Frechette, and Mihir Kulkarni, who have done the operations organization, Lindsay Reichelt from our marketing team, and then also Dr. Duncan Weston, who is our global head of R&D. With that, I'm immensely grateful to all the people who participated, and we will have presentations, video, all will be available for later retrieval online. Have a terrific afternoon or evening or middle of the night, wherever you are, and thank you for making this a part of your day. Good day.